Honestly,
Okay, I'll move the 2.1 assignments off a little bit so we can focus on debriefing here about the test a little bit, maybe today, and we'll see. Today will probably be enough, but we'll see how it goes. Okay, so first one here, and like I say, I apologize for this being so small, but I can't make these bigger for some reason with this math Excel stuff. We're just stuck with them being tiny. Use the graph below to determine whether the statements about the function f of x are true or false. So here's a little bigger version of the graph. Here are the questions we want to answer. We want to say, first of all, true or false? The limit of f of x as x approaches -2 from the right is 4.
yes.
So say it again, the limit of f of x as x approaches -2 from the right is 4. Yeah, that's true, isn't it? Right? Everybody agree? Okay. Maybe we can't. Anyway, it's true.
It's not calibrated.
What's going on here?
It's probably
Oh, I can write on it. Huh. It's weird, I can't do this. Oh well. Fail. I don't know what's happening.
Clayton, what are you doing?
Oh, I think it's because this thing's up there. Now I bet I can. Yeah, there we go. Okay, I got you. That's it. Okay. That's it. All right. Okay, so next one. The limit of f of x as x approaches 0 from the right? Left. You can see it on here. Yeah, from the left is 5. That's false, isn't it? Yeah. Okay, makes sense. Even though the value of the function there is 5, we don't care about the value of the function. We care about where the ant thinks he's going to step. So what is the value of the limit of f of x? Yeah, 0. Yeah, he thinks he's going to step there. Doesn't matter if he actually does, right? Okay, next one. The limit of f of x as x approaches 1 from the left equals the limit of f of x as x approaches 1 from the right. No, I meant 0. I'm sorry. I meant 0. Let me say that again. I didn't get a lot of sleep last night. I'm a little goofy here. The limit of f of x as x approaches 0 from the left equals the limit of f of x as x approaches 0 from the right. True. Everybody agree with that? So the ant anticipates stepping on the same spot from both sides. Very good. Okay, so I got to close that for a second. Scoot this down. True or false, the limit of f of x as x approaches 0 exists. Okay, now that's true, and that leads from the last statement, doesn't it? If the one-sided limits exist and agree, then the two-sided limit, the regular limit, works, right? Okay, because the ants from both sides anticipate stepping on 0, that's the value of the limit. And that's the next question. The limit of f of x as x approaches 0 is 0? True. True. What did we get up here? We got true, false, true, right? Okay. The limit of f of x as x approaches 2 is 4. Okay. False. Now why? You're correct, but I want you to tell me why is that?
It's from different directions.
Okay. That's only the limit from the left. Good. Limit from the right is what? 0. Yeah. Okay, good. So that's false. True or false, the limit of f of x as x approaches 4 from the left is 4.
Probably true.
Oh, that's wrong too, isn't it? Yeah. Okay, good. So then those are both false. Okay? Ooh, what do I do here?
Next question.
Next question.
Oh, I got you.
Ooh, you get some attendance.
Oh, okay. So it's not going to let me. Yeah, so I'm going to skip around anyway, because there were some that were. I mean, there's some of these people that all 17 people got one of these right. We won't go through that one, but here's one that looks like maybe we could take a quick peek at. Oh, that's new. Still doesn't make it any bigger though, does it? Okay, what about this one? I'll write this bigger. The limit of x sine x as x approaches 11.6 pi. We want to find that by direct substitution. Now, I would argue that this one should be a really simple one.
Yeah.
Okay. But maybe, is this, it wasn't 100% on this. I mean, there were a number of people that didn't get this. Is it a unit circle issue? Is that maybe what's happening with these?
Yeah, he's like, I don't remember the unit circle.
Okay, why don't we take a little,
I've been guessing.
why don't we take a second here and just do a brief review of the good old unit
I
circle?
told you like unit circle. I was like, you give me dough.
I remember this one.
See, I get a $100 on this there. I'm like, no problem. I'm like, oh. What did you say? Dude, give me dough. Probably.
I didn't.
It's like a very well.
Fine. I got
Where are you
it.
going?
That's a pretty good circle.
When?
You have a wet place.
Yeah. Well, yes.
Yes.
Oh, that was fun. What were you there?
I was there.
Oh, you were?
I was at 9 years.
Oh.
Took PJ's chair.
Oh.
That's
Okay.
right.
I remember you over there.
Right.
You were very quiet.
You remember?
Not really. Not all the time.
Oh.
Well, you never ask questions.
That's the most reasonable answer.
Okay, so
Why don't you?
More reasonable to ask questions.
I see what's going on here.
okay, let's talk unit circle. 'Cause I can give you a really quick, a couple tricks on the unit circle that will make it much easier for you.
I got you.
Okay, first of all, if you know quadrant 1 in the unit circle, essentially you know the whole thing. And you can very easily fill in all the blanks, right? So we're going to focus on quadrant 1 and then just take a second, just kind of reminding ourselves, how do I use that to fill in the rest of the blanks here. So in quadrant 1, x and y coordinates are both positive, right? Let's first of all just remember the whole point of the unit circle. Circle with radius 1, and for each of the points on the unit circle, we're going to define an angle in radians, which is actually just an arc length in radians, but it correlates to an angle, and that's how we want to think of it. And then we want to think of the x and y coordinates of the point on the circle at that angle. In other words, if we were to send a ray from the center out at a certain angle, wherever it intersects the unit circle, those coordinates are important to us, right?
Yep.
So the easy ones, of course, are the ones on the axes. So for example, right here, that is how many, well, what's my angle? 0, okay. And there really isn't we put a little degree symbol for degrees, there really isn't anything you do for radians. If you want to remind yourself, you can put just a little r to remind yourself that you're in radians, but you shouldn't. It's a unitless quantity. So that's 0, and what are really it's just 2 pi or 4 pi, right? I mean, it's any multiple of 2 pi.
Yeah.
But if we're going to stick, let's just say in the first lap of the unit circle, we'll just call it 0. Okay? What are the coordinates there? Say it again. 1, 0, okay? Now, which of those goes with sine and which goes with cosine? So just in general, if I've got some angle theta, the x coordinate corresponds to cosine or sine? Cosine, good. And alphabetical. C before S, X before Y. Okay, right? So in other words, the cosine of 0 is 1, the sine of 0 is 0. Okay? What's our next angle up here? What's the first one we hit? Oh, I guess let's write these in degrees too. So we got 0 degrees or 0 radians. Okay. What's this one going to be?
30.
Okay, it's 30 degrees. How many radians? Pi over 6. And the coordinates are,
I don't remember.
okay, this is where people have a hard time. Now here's how you can easily remember these. There are only 3 numbers that, other than 1 and 0, that ever show up on the unit circle. They're absolute values anyway. The numbers are the square root, well actually 1/2, the square root of 2 over 2. Yeah.
Root 3.
And the square root of 3 over 2, right? And in order, those are their magnitudes in order, aren't they? 1/2 is the smallest, square root of 2 over 2 is in between, and square root of 3 over 2 is pretty big, right? Closer to 1.
Yeah.
Okay? So you know that you're always building, first of all, you're always building a Pythagorean triple out of these things, a Pythagorean relationship, because this is a right triangle, isn't it?
Yeah.
Right? The x and y coordinates here really are just the legs of a right triangle, and the hypotenuse is always 1. So one thing you can always remember is just that, for example, here, I know that that this squared plus this squared has to equal 1, right? Okay. Now you know that this one is kind of skewed towards the x, right? So that's going to have a big x coordinate and a small y coordinate. Whereas this one right here, this 45-degree angle has equal magnitude x and y components, right? Because the slope is 1. Make sense?
Yes.
So then what's that going to do? Well, it's going to pull the x coordinate is going to get pulled from the middle one out to the big one. And the y coordinate then has to get correspondingly pushed to the small one, right? And so we end up with coordinate square root of 3 over 2 and 1/2, and we can show real easily that if we do that, that works, right? They obey a Pythagorean relationship. What's 1/2 squared? 1/4. What's the square root of 3 over 2 squared?
3/4.
3/4. What's 1 squared? 1. So 1/4 plus 3/4 equals 1. See, it works. Okay? Right? See how this is? And so you can really pretty easily, even if you're drawing a total blank, you can reconstruct this thing pretty easily. Okay, so we know that the coordinates here are square root of 3 over 2, 1/2. Now if we continue to move on up to 45 degrees, which is how many radians?
5/4.
Pi over 4. What's going to be the coordinates there then? Yeah, it's got to be the square root of 2 over 2, square root of 2 over 2. And you can remember that easily because square root of 2 over 2 squared is 2/4. 2/4 plus 2/4 is 1, right? That's what makes this. So you know that the two middle ones go together and the two extreme ones always go together in the unit circle. And then when we shift up to the top one, which is 60 degrees or pi thirds, then it's got to be small x, big Y, right? Okay, make sense?
Yeah.
See how that works? And then the top one, this is pretty straightforward. Top one, we know that's 90 degrees, pi over 4, and that's got to be 0, 1, right? And so all you have to do then, if you're in any of these other quadrants, all you have to do is just compare the 3 interior points to these 3, right? Like, for example, this is kind of an awkward one, the quadrant 4. Let's jump down there and take a quick look at that one. Okay, so if we're looking in quadrant 4, let's get rid of him. If we're looking in quadrant 4, these are our 3 interior points, right? And are the angles, if you're wondering how to get the angles, there's always a changer that allows you, if you're unsure, if you didn't remember that that was pi 6ths and pi 4ths and pi thirds, how do you translate from degrees to radians? What's the multiplier you use? Because you can probably remember the degrees pretty easily, right? 30, 45, 60, 90. You know this is 360, so those are pretty easy to recreate. Yeah, okay, good. You multiply by pi over 180. Yeah, if you ever want to find out what the radians are. You can't remember what they are. So 30 times pi over 180 is just 30 over 180 is 1/6, so 1/6 pi, right? That's how you can always get those angles. So what about down here then? Let's say I wanted to know, I'm going to fill in the blanks right here. Well, what's that angle going to be? How would you know? If that's a 30-degree angle right there.
60 minus 30.
Okay, good, good. So then I know that however much I'm increasing there, I'm going to back off from 360 that much here. I'm going to subtract 30 degrees, or better yet, I'll subtract pi 6 from 2 pi, right? And so that leaves us with 330 degrees, or what is 2 pi minus 1/6 pi?
11.
Yeah, so that's 12/6 pi. 2 pi minus 1/6 pi is 11/6 pi. Okay, and if I want to get the coordinates here, well, compare these two, right? They're just reflections over the x-axis, right?
Yep.
So wouldn't you agree that this is positive big, negative, or, x big, positive, y small, negative?
Yeah.
Right? And so I know what those numbers are. The big one is the square root of 3 over 2. That's positive. The negative small one has to be a negative 1/2. So I got it. And just using that same logic, we can fill any of these in. What if I wanted to find this one right here, for example? Okay, that's going to be pi plus how much?
Pi over 6.
Pi over 6, right? Okay, so that's going to be pi plus pi over 6 would just be 7/6 pi, right? And if I wanted to do the coordinates then, isn't this one going to be big negative x, small negative y?
Yes.
So that would be negative root 3 over 2, negative 1/2.
Yep.
Right? And so, that's, you can always just draw one of those things and don't have to fill the whole thing in. Just fill in the parts that you need. Just fill in the first quadrant and then fill in the parts that you need.
Yeah.
Does that make sense?
Yes.
Okay, does that help? Okay.
Maybe.
So, where were we then? Was I? Here. Okay. So then what about this? So the limit of x sine x as x approaches 11/6 pi. So on my unit circle, and there's my unit circle. I just know that I'm at that spot right there, right? So what if I evaluate directly, what is the sine, the y coordinate of that point? Negative 1/2. So when I evaluate directly, I just get 11/6 pi times negative 1/2, and that's my answer. Okay, so I can simplify that. So what do I get then?
Negative 11/12 pi.
Good. That's it, negative 11/12 pi. Okay, make sense?
Whatever. I know. You don't need to tell me.
All right, moving on. Let's see, it's another one. Okay, here was another one that seemed to be a little bit of trouble.
Oh, like it's all scrambled.
Looking at my hand.
Oh gosh.
Boy small. Boy begin.
Okay, what do we do with this one?
Boy begin.
Conjugate.
Conjugate, very good. So we're going to multiply this guy by the conjugate of the top, right? Top and bottom, which is what?
Square root of x minus 13 plus square.
Square root of x plus 13, right? The only, okay, now, and that's important that's a common mistake. Remember, the conjugate, all the conjugate does is changes the operator between the two terms. That's it. None of the other signs change. So square root of x plus 13 minus square root of 13 divided by itself. Plus 13, sorry, there you go. There we go, okay? And if I do that, what do I get on the top? Okay, I'm gonna get x plus 13, first times first, right? Minus 13, okay. Because remember, when I multiply conjugates, the O and the I always cancel, the cross terms always cancel. You could FOIL it out, but you don't have to, they're always gonna go away. It's just gonna be the first squared minus the second squared, always. And then on the bottom, I get kind of a mess. Now it's x times that whole quantity, right?
Yeah.
Okay? And so, what happens? Okay, good. The 13s cancel horizontally. Plus 13 minus 13 goes to 0. And then I just end up with that x over that x, right? And so I can vertically cancel. Now, do they go to 0 or 1 when I vertically cancel? 1. So I get a 1 there. And now I can evaluate my limit directly. Now if I let x go to 0, on the top I've just got 1. That's all that's up there anyway. On the bottom, if x goes to 0, I get square root of 13 plus square root of 13, which is 2 squared. That's it.
Yeah, where'd the X go? Oh, yep, I'm seeing it. Gotcha.
Okay.
I got this problem right, okay, but.
Okay, so that's good, that's good. Let's see, what else? What else? Okay, here was, oh, here's a couple bad ones.
You don't see it. That's 0.
Okay, this was a bad one.
Really?
Oh.
Is this, now just you guys stop me if this is this a good way to go about this? If I just kind of pick them up?
Oh, yeah. Oh, yeah.
Very much so. This is how.
Very much so.
Okay, good.
Had nightmares like this. The tans to the sides.
Okay, so what about this guy now? Once again, what do we always try to do first?
Direct substitution.
Yeah, direct substitution. And if we do that, I think we may have actually even gone through this one, but that's okay, we'll go through this again. If I evaluate this, unit circle time, pi fourths is just 45 degrees, right?
Yes.
Okay, now when you see a tangent, you're just taking the ratio of sine over cosine, right? So that's going to be 1, isn't it? 1 minus 1 is 0. Sine and cosine have the same values at pi fourths, so we do get 0 over 0, right? So we know that this is indeterminate. We've got to do something to it. Okay, now this however, we only have 2 special trig limits, and both of them are defined when x goes to 0. So neither one of those is really going to be what we need here. This is going to be a case of really just simply trying to get some cancellation of factors. Does that make sense what I just said?
Yeah.
And if we write down those 2 special trig limits, remember we had the limit of sine theta over theta as theta approaches 0 is 1. Good. So there's one of them. Do you remember the other one?
1 minus cosine.
There you go. Good. 1 minus. I can't read that. 1 minus
I can't read that.
cosine theta over theta as theta approaches 0 is 0. Very good. Okay. Good job. So we got those, but neither of those are going to apply here because in both cases our angle is going to 0. So what do we do in this case when we see a problem like this? And there's a definite strategy.
We change the tangent to
Good. We always want to rewrite the tangent in terms of sine and cosine. So it's going to look like a fraction on the top, and then it just becomes a lot of simplification. Remember, then our goal is just to get the top into one big fraction, bottom into one big fraction, flip and multiply, right? So on the top, that just looks like 1 minus sine x over cosine x. Bottom already looks okay. See, what else do we need to do on the top? Common denominator. So my common denominator will be cosine, right? What am I gonna get over cosine on the top? Oh, okay, everybody see that? Cosine minus sine all over cosine. I can check it real easily, right? If I just distribute the denominator, cosine over cosine is 1, sine over cosine is sine over cosine.
How did you get that cosine
Really?
on top?
Because I need to get a common denominator, so I'm just multiplying this one by cosine over cosine.
Oh,
Okay, make sense?
Yeah.
Oh, he sucks to write.
Now, once you write a fraction in terms of a common denominator, I would encourage you, instead of writing that in-between step of cosine over cosine minus sine over cosine, you know that your goal was a common denominator, right? So just write one denominator. Does that make sense? See what I'm getting at? You guys are getting sophisticated enough with your algebra. You can kind of crunch those steps together a little bit. So, so we get all that stuff. There's our top fraction divided by sine x minus cosine x over 1. So now what?
Flip.
Flip and multiply. Good. So we got the top one. Times 1 over sine x minus cosine x. Now you guys are really good at this. I've noticed that this is, what do we do here? We want to try to get cancellation, but it doesn't quite cancel yet. Okay, good. Everybody see that? I need to, in order to make this look like this, I have to factor out a -1. So it becomes negative the quantity sine x minus cosine x. Right? Everybody see that? Okay, and now we get our cancellation. Right? Sine x minus cosine x cancels top and bottom, and I just get a -1. Right? And now we can just evaluate directly. So we're left with the limit of -1 times 1 on the top. On the bottom, we just get cosine x times 1. As x approaches pi-4ths, well, what's the cosine of pi-4ths? Square root of 2 over 2. If we flip and multiply, I just get -2 over the square root of 2, which reduces to
Negative square root of 2.
negative square root of 2. Does everybody see that?
Actually, I can't see it. Brian said
Right? 2 divided by the square root of 2 is just square root of 2. Because square root of 2 times square root of 2 is 2.
it is indeed.
Okay? All right, so that was commonly missed. Let's find another one. Okay, this was very commonly missed. This was a big daddy of problems.
Oh, I see we got it.
What does this mean?
Okay, the good news. Good news is this is a really easy problem. Bad news is a lot of people couldn't at the time remember what it was all about, but I'll remind you. Okay, this is one notation. Yes, ma'am.
Oh, I remember so stuff this spelling.
Oh, okay. Oh, you got it.
I did that
Good.
a lot too.
Good, good.
I did that a
Okay,
lot
so
too.
int
Just put it out
x, that's one notation we have for it, but a more common notation is, I think what we talked about in class maybe instead, was this.
Oh, yeah.
Remember that?
Yeah. Yeah.
But they mean the same thing.
Yeah.
It's a great, int x, and that's what it'll be on computers or your graphing calculator. It'll show up like that if you go to the math menu. That just means greatest integer function. So this is that step function, right? And remember, the good model for this one are the beads, where you put the knots on the x, y, or on the x-axis, the knots are at the integers, and you always slide a b to the left until it hits a knot, right? And that's the value output of the function. The way of saying that would be the greatest integer function is the greatest integer that is less than or equal to x, right? Less than or equal to. So the greatest integer function evaluated at -7 would be -7. At -6.9 it would be -7. At -7.1 it would be no, -8.
Oh.
Yeah, so we'd have to slide down to -8.
Oh, okay.
Okay?
Can't go back, this is the knot, you gotta go.
Exactly, there you go. So if we're approaching then 3 from the left, we're actually approaching 3 from a number like 2.999, something like that. So what's the greatest integer that's less than or equal to 2.99? 2. Yeah, does that make sense? That's our answer. That's our answer, really. It's just that simple. And if you want to make the picture, you're welcome to do so, but I don't think you need to. Right? Here's the step function we create. Right? Remember that? Remember that? Yeah. Okay. So that's one that most people miss. That's an automatic. That's a gimme when you retake. That really is probably the easiest question on the test.
Probably. Well, that makes me okay. I missed the easy one.
Okay, so that to me that seems like that covered the ones that were the most egregious. Yeah. So we scoot to the next test.
Yes.
What's that? Yeah. Which one do you got? 1 over which one?
So we have like x equals this, right? And then it's open.
So on top,
X equals 4 open, right?
Yeah.
Okay. Yeah.
Let's say this right here is 3. Can you tell me? Yeah. 3 on the left. 2 because
Okay, Taylor, say that again. Taylor's got another request here.
okay.
So it's 3 on the right.
X plus 4 minus on the left is 2.
Yeah, I see that.
X.
Okay, as x goes to 0.
Yeah.
Okay, yeah. So this was, okay, this is one of those, remember we looked at a couple different, actually we looked at 4 different cases, non-trick cases. This was one of them where, this is one where there's really no special trick. It's not like we're going to multiply by a conjugate or we're going to factor and cancel factors. Actually, that's what it ends up being. But our strategy here is just to simplify until we can cancel common factors, right? So crunch the top into one big fraction, bottom into one big fraction, flip and multiply. And in that process, we're going to get probably what's the factor that's going to need to cancel top and bottom here. If we're having, yeah, it's going to be x, isn't it?
Yes.
Because when x goes to 0, x equals 0, right? And so we're going to have to somehow get that factor of x over x to drop out of here. And it will. Okay, so on the top, when we're going to add up these 2 fractions, we've got to get a common denominator. What's our common denominator going to be? Okay, good. 4 times the quantity x plus 4. The product of the 2. And then what am I going to get? I'm going to get something minus something else. What's the first term going to be? 4 minus. Okay, everybody see that? Okay, now you see how I wrote that too? That's a good way to, you see how we can kind of abbreviate that? Okay, on the bottom we've just got a plain old x, which we could write as an x over 1. So all we need to do now is just flip and multiply and then simplify the top still a little bit, right? So on the top, if I distribute the negative, I'm going to get 4 minus x minus 4. So what's that leave me with?
Negative.
A negative x. Okay, so we could just replace all that stuff with a negative x, right? So then I get the limit of negative x over 4 times x plus 4 times 1 over x
Yes.
as x approaches 0. And now I get my cancellation, right? Because we've got a product of fractions, I can cancel diagonally here, right? Like so. Make sense? Now I can take my limit. On the top, I've just got a negative 1. On the bottom, as x goes to 0, I get 4 times 0 plus 4 is 4. Okay? Make sense? Okay? All right, so maybe we'll take a peek at least I'm going to run out of time probably, but let's look at the graphing calculator test. Alrighty. Okay, here's one. Find the points of discontinuity of the function. Okay, and so we wants to know several things. Wants to know where the discontinuities are, and then of what nature are they. So.
Oh, yeah.
Okay, so let me grab this one. I'm going to put it on the big screen so we can manipulate it a little bit here. Ah, that's what I want. Okay. So now let's talk through this. What's the thinking behind this? Where are we going to get points of discontinuity?
0.
Okay, -2. Good. Yeah, and that occurs because I get a 0 on the bottom. Now I'm going to get discontinuities wherever I have zeros in the denominator, right?
Yeah.
Okay, but the nature of those we got to be careful about. In this case, when x, x is -2 is obviously the first answer. We have a discontinuity at x equals -2. What kind?
Infinite.
It's going to be infinite, isn't it? Because, and how come?
Vertical asymptote.
Okay, vertical asymptote. Now, how is that different from something like this? What if I had y equals x squared
Kind of, yeah.
minus 1 over x squared minus 2x plus 1. Where would the zeros at the bottom be now?
-1.
-1, right?
Yeah.
Okay.
I can't.
Where are the zeros at the top?
-1.
-1 and +1.
Cancel.
So if we have a simultaneous 0, top and bottom, what's that going to be instead of a vertical asymptote? Right? Because this really this breaks down to x minus 1 times x plus 1 over, to make this easier, what if the bottom had just been x minus 1? You see what I'm saying? Because those cancel, that would be a whole instead. Now, -2 is a 0 at the bottom, but not the top. So it has to be infinite. Yep. Okay. All right. Well, I'll move that date back for 2-1. We'll wrap this up tomorrow, and then we'll move into. How's that sound?
That sounds wonderful.
And then you guys can do retakes this week if you want to. How about if I make the 2-1 assignment due like Wednesday or something, just because we're getting interrupted with this stuff. So I'll give you some extra days on it.